Okay, so let's start our introduction of MCNF. So we will first talk about the general ideas, and then we will look at the LP formulation, and then finally see how other type of network flow models are the special case of MCNF. So we start our introduction by giving you some notations or terminologies. So very quickly, let's see what are them. We're talking about networks, and in a network or graph, we always have nodes and arcs. Sometimes nodes are also called vertices, so these are the nodes, okay, or points. And when you connect nodes with arcs, edges, or links, then somehow we form a network, okay? So a typical interpretation is that nodes are the locations for markets, for factory, for distribution centers, and arcs are roads that you may go through, all right? So arcs may be directed or undirected. When we say there is an arc from U to V, if we include UV in a pair of parentheses, this means we say this is a directed arc. If we use instead a pair of square brackets, then we say this is undirected. For this lecture, all the arcs are directed. Somehow that means moving from A to B and moving from B to A is different. Maybe A to B is possible, but B to A is not. Maybe both are possible, but they have different cost, they have different capacity, they have different routing time. Okay, so somehow arcs from A to B and B to A, they are different. So a network is directed if its arcs are directed. So in this lecture, we talk about directed networks. An undirected network by some people are called graphs. Okay, so for some people, a network is by nature a directed network. A graph is an undirected network. I won't say all the people are using this kind of terminology, but sometimes you see it. So now with this definition, we are able to define the so-called path or route. Path or route is a collection of links or arcs, okay? So a path from S to T is a set of arcs, S to V1, V1 to V2, to VK minus 1 to VK, and then VK routes to T, something like this, S to V1, V1 to V2, V2 to V3, and V3 to T. So that all these things are connected. When we say connected, that typically means we are able to go from S to T by passing through all these arcs. All right? So in this case, this path has a source, which is called, which is our S, and a destination, which is our T, and obviously direction matters. Okay? A cycle, which is sometimes also called a circuit in some textbook. A cycle is a path where the destination and the source are the same one. Okay, so if you go in this way, then you have a cycle. A path is a simple path if it is not a cycle. Okay, so when you see a simple path, this is not a cycle. Finally, a network is an acyclic network if it contains no cycle. So what does that mean? Suppose we have a network like this. Okay, so this network is acyclic because there is no cycle. Okay, there's no cycle. If you have this one, it has no cycle. How about this? It has no cycle. How about this? In this case, you have a cycle. So you may route from here to here to here. In that case, this is a cyclic network. So let's define more terminologies: flows, weights, and capacities. A flow on an arc is the action of sending some items through that arc. So when you have an arc, you may have a flow on it. And the number of units you send through that arc is called the flow size. If I ship 5 products through this arc, then the flow size is 5. A network flow is a collection of all arc flows. Okay, so whenever you have a network, something like this, if you say, okay, I'm going to transship this through this route 5 units, through that route of 3 units, and maybe also through this route 2 units. If that's the case, then in total from S to T you send 10 units, and collecting all of this gives you a network flow. Okay, so a network flow can be considered as a solution. It's a plan for making flows. Okay, each arc may have its weights. In many cases, it mentioned about distance, cost for unit flow, and so on and so on. Okay, so typically that represents how expensive it is for you to ship 1 unit from here to there, how much time it takes, and so on and so on. So a weighted network is a network which you have weights on arcs. Okay, an arc may have a capacity constraint. That means there may be an upper bound or lower bound for its flow size. Okay, so it's possible that you may ship items from here to there, but you have only 1 truck or you have only 1 flight. So in that case, the number of items that you may ship is upper bounded by the capacity of your carrier. Right? The lower bound is seldom mentioned. It's typically 0. Okay, but in some special applications, you also have the lower bound limitations. Finally, a network is called capacitated if there is any arc that having some capacity constraints. In that case, we say your network is capacitated. So now we are almost ready to define our minimum cost network flow problem. Let's consider a weighted capacitated network. We call this network G as a collection of V and E. V and E are a set of nodes and a set of arcs or edges. Alright? So we somehow need to define a graph by drawing the topology and by specifying the connections or the relationship between nodes and arcs. Okay. For each node I, there is a supply quantity Bi. Okay, so you may think about this as supply quantity, demand quantity. So when Bi is positive, there are some units on hand that you may ship out from this particular node. So that's a supply node. Consider that as factories. When Bi is negative, that means you need to ship something into this node. Or you may consider them as markets. And finally, there may be some transshipment nodes where you have no supply quantity. In that case, this means they are just transshipment points. Okay, you go through here, you go through there. It's not a market, it's not a factory, but it's somewhere that you may, for example, a distribution center may help you do the transshipment or transportation. Okay, for each arc, Ij, the weight is called Cij. Cij is typically set to positive to be the cost of each unit of flow. So it's not always that it is non-negative. Sometimes you may see a negative cost. But in general, in typical cases, you see a positive cost or 0 cost. Okay? That's the cost you need to pay for each unit of flow on that particular arc. So now the question is clear. We somehow need to satisfy all the demands by having some shipping plan from our supply nodes to destination nodes. And then we want to do that in a minimum cost flow way. Okay, so all these nodes are subject to your consideration. You may want to decide how to ship those products, but somehow there are costs. So you want to avoid expensive links. And the cheap links may not also be useful because they may have capacity constraints. So this overall, the consideration is forming you a minimum cost network flow problem, which is abbreviated as MCNF. So here is an example. In this particular example, these numbers put into inside a pair of parentheses. That's a label that labels the supply quantity. So very quickly we can see this is a supply node because there are 25 units to go from here. There are demand nodes, the first one, demand nodes, the second one. They require 10 and 15 units. We also have these transshipment nodes. Transshipment nodes, they don't require anything and they cannot generate anything. On each arc, we have Uij and Cij, which means the upper bound and the cost. Okay, so here you may move at most 15 units. For each unit, you pay $4, and so on and so on. Sometimes you may see there are some arcs, they don't have capacity constraint. So that means the route is very easy to move along, and there is no capacity constraint on it. It's possible. Okay? So between two nodes, there may be two arcs of different directions, as we previously mentioned. So you may see here, between node 3 and node 5, there are actually two links. Okay? It's possible that sometimes both links are used, and you may see that their capacity are different and their costs are also different. So it's always possible. So by looking at this, maybe we would like to see whether there is any feasible plan we may find to complete this flowing plan. So for example, here we need 10 units. We have 25 here. So how about we ship 10 units here and 10 units here? So we may satisfy the demand at node 4. Here we need 15 units. So maybe we ship 15 units here. That sounds good. But note that here, along the arc from 3 to 5, we cannot ship 15 units. We don't have that amount of capacity. So maybe from here to here, we may ship only 10 units. Well, if that's the case, what should we do? Oh, don't worry too much. Because from 3 to 4, there is another link. And through here, we may ship another 5 units. And then we also move from 4 to 5. Then this is a feasible flow. But of course, maybe this is not an optimal flow, right? Because there are always other options that we may find. So here, we need somehow a formulation, maybe a linear program, maybe an integer program that help us solve this problem to find the minimum cost network flow. Later, we will see how to do this.